Hi, do you remember Derek of Veritasium made a video posing an electrical question? And everyone, including me, were fuming over it?
Now the question is, after I close this switch, how long would it take for the bulb to light up?
Well, now he made a new video on the subject. And I'm back, baby! Derek, in his second video, acknowledged that his original question was too vague and did a very good job clarifying a lot of details. Otherwise, in my opinion, almost all his answers could be correct. But, well, here I am, which means I'm not happy with all the details. I feel like we are not exactly on the same page. Mind you, Derek and I are friends. Hopefully he thinks the same. And he's one of the greatest YouTube science communicators, and his presence is very valuable, especially since his idea of science is not melting lipsticks.
Rewind needs more science. Could we do an experiment? Love that. Melting lipsticks.
Melting lipsticks? Melting lipsticks? We want more science. Melting lipsticks? This back and forth is not about who wins. It is about all of us understanding science better. And what better way to understand things than my sponsor Brilliant's interactive courses and quizzes? You can learn a ton of what you need for free signing up using my link brilliant.org/ElectroBOOM, and the first 200 people can also get 20% off Brilliant's annual premium subscription. Anyway, I decided to have a call with Derek and discuss, which would be much faster than making a video and waiting for his response. And less embarrassing too, in case I'm wrong. So let's call. You ready? So here I have my friend Derek Moller, who is a science communicator, filmmaker, television personality, and inventor. And of course he's a YouTuber at Veritasium channel with over 12 million subscribers. Don't you wish you had a friend like him? Now you can with a low monthly payment of $39.95. Just kidding, sir. So thank you for taking the call. I like to focus on 2 points that I feel I don't agree with.
Misconception number one is thinking that electrons carry the energy from the battery to the bulb. Misconception two, thinking that mobile electrons push each other through the circuit. I think those are both good statements. The point about electrons not pushing each other through the wire is specifically that the mobile electrons, so like the current carrying electrons, are not pushing into each other like, you know, marbles in a tube or like water in a hose.
So regarding the first point, the electrons pushing each other, I think we need to define pushing first. See, at this point, I'm thinking Derek might be thinking that pushing is only between the surface of the material and not between energy fields. Basically, an object pushes another object by exerting force to the other one. But in atomic level, the two objects don't actually touch, as in matter doesn't touch matter, because the electromagnetic interactions between their atoms keep them apart. So, we can define pushing as an object exerting force to another due to the repulsion of the electromagnetic forces between their surface atoms. And I guess the gravitational interaction of matters in larger scales.
Yeah, if you have two objects and you bring them close together, yeah, charges in and around the surfaces can apply forces on the other object.
Oh, he knows. Of course he does.
And I think, of course, it's important that there's sort of like a net force, right? Every electron in a wire will exert a force on every other electron in a wire. But the argument I'm making is that there are equal and opposite forces on every electron such that the mobile electrons are not actually pushing each other around. The main thing I like to think about the battery doing is maintaining this distribution of surface charges.
As in his video, here Derek explains that there is a gradient of seemingly static charges only on the surface of the conductor, and the density of charges inside the bulk of the wire is uniform, with number of electrons and protons being equal. So the charges inside the wire don't push each other to move, because the conductor is electrically neutral there, and the net force on charges from neighboring charges is zero. Derek claims it is the surface charge gradient that creates fields inside the wire, pushing charges forward. Why do you think that charge distribution is? What is the reason for that?
I think that charge distribution is set up
by the fact that there's a battery there. And so the battery has an electric field which influences the charges right beside the battery. And their electric field influences the charges right beside them. And their electric field influences the charges right beside them, and so on. And that's what sets up the surface charge distribution.
The way I always imagined how this all worked was that the battery just pushes an electron in the wire by its electric fields, and like a train, the electrons push each other forward, sending the current through. It has always worked for me and explains everything. But at the same time, I don't have a good reason to reject Derek's notion of surface charges. Why does it even matter either way? The charges are pushing each other forward. So again, back to the definition of pushing I was talking about, that it's in the atomic level, it's the electric fields and magnetic fields between the atoms that keep them apart. It seems to me that the electrons reacting with each other is causing them to move in the wire, right? And to me, it's pushing.
So the argument that's made, which is not my argument, but the argument that I relay to you, is this idea that, like, okay, we have an electron moving along here, another electron moving along here, and of course,
Right.
like the actual motion is like this, but
Right.
they're ever so slowly drifting this way if you net it out. And then there's kind of a question of like, okay, so why are they net drifting this way? Is it because this one's pushing this one?
Derek again explains that because of equal density of electrons and protons inside the wire, the charges are not pushing each other forward, which I still don't quite agree with. I think the sea of electrons is a bit compressed as it is pushing forward through the resistance of the wire.
And I think that's a fundamental disagreement. Can I read you something? This is from a physics textbook.
Yeah.
And there's a heading which says, electrons cannot push each other through the wire. As we've stated previously, there can be no excess charge inside a conductor. And we'll see later that this also applies to the steady state as well as to equilibrium. So the number density of mobile electrons inside a metal wire must be equal to the number density of positive atomic cores. The inside of the wire is electrically neutral. Rather, it must be other charges somewhere outside the wire that make an electric field throughout the wire that continually drives the electron current. And so this is my explanation for the maintenance of this current, is that there is a gradient of charge on the surface creating an electric field inside the wire that causes the electrons to go one direction more than the other.
So do you think if we have more, like a larger electric field through the wire, we will have more current?
Yes.
See, the thing is, if there is a charge gradient across the wire, it is because the wire is resistive, and this creates a voltage across the wire we typically want to avoid because it would waste energy. If the wire is more conductive, there is a smaller electric gradient and voltage across it, what results in more current through the load. Less electric gradient across the wire means more current, which is opposite to Derek's notion that the gradient creates current.
Oh, that's interesting. That's very interesting. That's
See?
very interesting. Yes, yeah, I hear you. You say it's bad for current. I say it's the thing driving the current.
Yeah, but how come when we remove it, we have more current?
But it's not an apples to apples comparison.
Derek explains we can have a certain resistive wire and place a voltage across it. Increasing the voltage, we increase the electric field gradient across the wire and therefore the current through the wire, which is opposite of what I'm saying.
Yeah, so I'm saying higher gradient, more current. You're saying higher gradient, less current, right? But it just depends on how you set up the problem.
Damn it, he's right. He's messing with my brain with truth and facts. But either way, no matter the mechanism of how charges flow in the wire, the charges are still pushing each other forward. Electric and magnetic fields around the wires are created by electrons, surface charges, or whatever you want to call them, in the wire, right? So why do we say they are not pushing against each other? Because it's them directly affecting each other.
I would agree that electrons push electrons, but I don't think that mobile electrons push mobile electrons. So I guess what I'm saying is the electrons which are forming the current are not pushing on each other. Yeah, I can send you this chapter of this book, which is basically exactly what I said in the video. So is the energy carried by the electrons or by the fields? And obviously the energy is delivered by the electrons. We all agree that the electron bumps into an ion in the load, transfers the energy like that.
It's a little bit confusing. Like I always had this traditional view of how electrons move through the wire.
Maybe it's a good sign that like there are different mental models, right? Different ways of seeing the world. And I think the model that we all learn about voltage and current is like very useful and very intuitive and works 99.9% of the time. So it's like, why even think about this, you know?
Well, the thing for me is that it works 100% of the time. I've never seen a case that it doesn't work. That's the problem.
I mean, what if you try to answer the question, like a kid asks you, like, okay, these electrons are coming here and there's a resistor down here and there's a resistor over here and this one is twice as big as that one. Right. So half as many electrons go down this path as that path. But like, how do the electrons know to go like half as many this way and twice as many that way?
Well, in my view, when you first close the switch, a wave of current is pushed through the wire and splits equally in both branches, although there are different resistances in each. But when the wave hits resistors, some of it reflects from them. There is a greater reflection from the higher resistance as the current can't get through as easily, which adds up to the initial wave resulting in less current through the higher resistance. So initially the charges don't know which branch to go more into. But because of this constant feedback from the loads, after this transient state passes and things settle, less current can go through the higher resistance.
Yeah. I don't know, is it a worthwhile distinction to say, is it the electrons in the wire, like in the bulk of the wire, which are creating this electric field, or is it electrons on the surface of the wire? I don't know. Is that a worthwhile distinction to make?
Well, it's good to know the truth, of course. But it seems to me that the traditional way of thinking, although it may be wrong, doesn't seem to have any effect on the outcome of what you're trying to do in the actual circuit.
Right. I mean, I think that's the power of it as a model. Like, it's such an effective way of thinking. Yeah. Like, why would you ever change your mind?
Thanks for the call. Bye. I thought it was an open and shut case, me being so smart and all-knowing. But damn, he makes some good arguments. So, the charges don't push each other through the wire? The thought around charges wouldn't let go until one restless night when I had too much tea and couldn't fall asleep. Thinking about charges, suddenly everything clicked. Oh shit! Keep it down. Derek was right about the surface charges, but at the same time, I'm still right. Charges do push each other through the wire. I need to talk to Derek again. Thanks for taking the call again, and thanks for the chapter of the book you sent me to. I read it last night, and for the most part, I believe it just agreed with what I thought during my restless night, which was good. Let me explain more clearly how charges flow in the wire. Let's just use one resistive wire, initially not connected anywhere in equilibrium, as in positive and negative charges are equally distributed. Suddenly, we place a battery across the wire, which with its electric fields pushes some electrons into negative and sucks some from the positive. Just remember, electric charges are super strong and it doesn't take much to make a lot of current. So in reality, you would see close to zero charge movement. This is exaggerated so you see things better. The excess electrons repel each other in all directions, but vertically they can only go as far as the surface. Horizontally, a lot of them move forward, which again repel each other in all directions. Some more end up at the surface and the rest move forward. Similar distribution happens on the positive side too, except there the positive charges don't move, but rather electrons are sucked into the positive areas. So we end up in a charge distribution like this, on a very thin layer of conductor surface, and the rest of the wire is electrically neutral, like Derek mentioned. And charges there have a net zero force on them from the adjacent mid-wire charges. Now let's take an electron in the middle and see the surface charge forces on it from 4 close corners. Surface is more negative here, so we have strong repelling forces. Surface is less negative here, so we have weaker repelling forces. This makes a net forward force on electrons in the middle. We see the same forward force on all the electrons inside the conductor. So Derek was absolutely right. Inside charges are pushed forward by the surface charges only. All good and dandy so far. But I did some extra analysis on the surface charges, like this one. Strong repelling force from these two corners and weaker repelling forces from these two, so we have a net force pointing up and right. We do the same analysis, and right in the middle, the force is to the right, and in the positive side, it is to the right and bottom. It makes sense. Excess electrons are pushed to the surface on the negative side, center is equilibrium, and on the positive side, they are sucked to the middle. But there is also a horizontal force on all the surface charges, which means they also move forward through the wire. They are not static charges, as Derek initially pointed out. The only thing static about them is their distribution over the surface. Of course, the positive charges don't move to start with. We assign a movement to them opposite of the electron movement. And because electrons move this way, we assume positive charges move that way. Like, what would stop them from moving forward? That's the question. Is there a reason for them not to move forward when there is a force applied to them?
That's a very good question. And I don't know that I have a good answer for you. And you're extending that to say, well, the surface charges are moving as well.
Yeah, they are also the current carrying charges, right?
Yeah. So the author of the textbook wrote to me about this specific question. Okay. It is rather common for students to ask whether the surface charges contribute to the current. Obviously, the positive surface charges don't drift. I don't know anything about whether the electrons are bound or not in surface states, but it's easy to see that even if the surface electrons do move, they will make an utterly negligible contribution to the current.
Right.
So the argument is are they bound in some sort of surface states?
I would say no. But I mean, you and the author of the book don't know. And there might be a reason for it that they actually don't drift. And I don't know. So I guess that's another video for you to figure that out. See, the surface charges are a very negligible portion of the total current, but they are so strong they create the entire current through the wire, and they also seem to be pushing each other forward. So the battery does the work by replenishing the surface charges, pushing electrons into them and sucking electrons from the other side as they go through the circuit. And surface charges act like the conveyor belt that carries the middle charges forward. So I feel like that much force between them compensate for no force in the middle charges.
In the case of our thought experiment with this battery and a switch, the long wires and the bulb, when you close the switch, why is there any energy at the bulb at all in like 1 meter over C seconds, right? Like, why is there energy there at all? It's because of fields. Like,
yes.
And you could say, well, it's because electrons over here are pushing electrons over there, which is also true, but they're pushing each other through a long range interaction, which is a field interaction.
Well, it is always the case. Like, electrons never, it's always a field interaction. It doesn't matter if it's close or far, right?
Yeah. I guess if it's a close range interaction, I'm more comfortable with saying like, oh, this electron pushed that electron and that electron pushed that electron. You know, if it's a close range interaction.
Yeah, you can't discriminate like that. It's always fields pushing against each other, close or far.
Yeah, it is that question of like, I don't know, is near field versus far field, is that a worthwhile distinction to make? And that's really what this question was meant to tease out. It was meant to tease out the question of like, do you think that electrons in the wire are physically sort of carrying the energy, or is it the fields around them which carry the energy? And I think that was the point of the thought experiment.
Right. And I don't disagree with you. I just think that both of our thoughts exist together. None of them is wrong.
No, I think
electrons and fields are existing together in the same environment, right?
Yeah. Let me ask you this question. In a traditional way of teaching circuits, you would say
Right.
the charge comes along, drops off its energy in the load, and then goes back to the battery. And you
Right.
could ask a question of the students like, okay, so which way are these electrons carrying energy as they come back to this battery? And I don't know if the answer would be like, well, they're not really carrying energy. They're at a zero potential now, so they're just basically completing the loop or whatever. I'm not sure if that would be the answer. But if you look in the field way and you think about pointing vectors around the wires, what you see is
Right.
that both electrons going to the load and electrons coming back from the load are both carrying energy through the fields to the load. So I would say
Right.
there's a qualitative difference, at least, in how you view the flow of energy, depending on whether you take a field view or you take a like electrons pushing electrons going around a loop
Yeah,
view.
but I can always refer back to my bike chain example, right? Both the chains leaving the front pedal and coming back to the front pedal are contributing to the energy placed in the back wheel, right?
Yeah.
Well, I mean, in a bike, when you pedal, the top chain is rigid and the bottom chain is slacking. But imagine a system that the bottom chain was rigid and could also push, or a closed-loop water pipe that water flow could both push and pull. Both acts of pushing and pulling are transferring energy to the load. And that's what electrons are doing. They are, on one side, you're pushing them into the load, on the other side, you're pulling them away from the load.
That's nice.
In both cases.
That's nice. That's nice. I like that. And if we add the idea that like the pulling and pushing is done through long range field interactions, then
Yeah.
I think we're fully in agreement.
Yeah, I think that's the case. And then we are fully in agreement.
But yeah, I think like my motivation in making both these videos was to reflect on the fact that I was taught and I taught circuits in a way
Right.
that certainly didn't understand these nuances.
Right.
And you know, it was that surprise that led me to make the videos. That
Right.
excitement, yeah.
Well, it was an eye-opening conversation for me thanks to Derek. He is one smart dude. But at the end of the day, I think my view of charges pushing against each other, transferring energy from the source to the load works because I never look at charges as marbles banging against each other. I always see charges and fields as one package where fields can extend forever. I would say the only difference between my model and reality was that where I thought charge gradient was distributed throughout the entire wire, in reality they were distributed over the surface. They still push and pull each other and the outcome is the same. And I'm not done! I bought a whole ton of cables and I'm gonna do Veritasium's original test with the longest loop of wire ever done in the history of mankind on YouTube probably. So subscribe for that and definitely check my sponsor Brilliant to make sure you have all your fundamentals in math, science and computing in good order so you won't end up making wrong assumptions. Either if you're on your computer or your phone, Brilliant has made it fun and engaging to learn by interactive courses and quizzes. It's not just a brain exercise, it gives you fundamental, real-life knowledge you can use at work or school. For example, if you like to understand electronic spatial field strength or charge distribution, the vector calculus courses are some of the best places to learn about vectors and math required to understand them. And in the best way too, you don't just read, you interact with your courses. You move things around and see what happens when you change something. This is the best way to keep your attention and make you learn. You can just start trying Brilliant for free, signing up at brilliant.org/electroboom, where the first 200 people can also get 20% off Brilliant's annual premium subscription and get full access. So do it, and thank you for watching.